All right, let's go on a journey. We're heading to the very bottom of the temper scale, to a place so cold it basically breaks all the rules of our everyday world. We are talking about absolute zero.
You know, it sounds like a simple question, right? But the answer is one of the most fascinating and frankly bizarre stories in all of physics. So, what is the ultimate cold? Is there a hard limit to just how low we can go?
So, that limit has a name: absolute zero. On the Kelvin scale, it's a nice clean 0 K. For the rest of us, that's a ridiculously cold minus 273.15 degrees Celsius or minus 459.67 Fahrenheit. The theory was, at that point, a gas would have zero pressure and zero volume, which of course is a physical impossibility, and that right there was the first hint that we were dealing with a fundamental limit of the universe. Now, getting to this theoretical floor wasn't just some abstract idea. It became one of the great races in scientific history. It was a quest that spanned centuries, all to see who could get to the bottom of the thermometer first. It all started as just a thought experiment way back in the 1700s. Fast forward to 1845, and the legendary Michael Faraday gets us part of the way there. He starts liquefying gases and hits minus 130 Celsius. Then the race really heated up, or I guess cooled down. James Dewar liquefied hydrogen in 1898, getting us tantalizingly close at just 21 Kelvin. But the final prize, the Everest of cold, was liquefying helium, and that went to Heikki Kamerlingh Onnes in 1908. He reached an incredible 1.5 Kelvin, and yeah, you better believe he won a Nobel Prize for it. But, hold on a second. Did you notice something? They got incredibly close, but nobody ever actually hit zero. So what's stopping them? And more importantly, what's stopping us from taking that last tiny little step? Well, it turns out the universe has put up two major roadblocks. And the first one is baked right into the fundamental operating system of reality: the laws of thermodynamics. Okay, think about it like this. Cooling something is really just removing its heat energy. Easy enough. The first chunk of heat is pretty easy to get out. But as the thing gets colder, trying to remove the next chunk of heat gets a lot harder. And as you get infinitesimally, incredibly close to absolute zero, it becomes infinitely difficult to remove what little heat is left. This whole idea is the core of the third law of thermodynamics. You can walk towards zero forever, but you can never, ever actually arrive. And this isn't just, a guideline. It's a core principle of physics, sometimes called the unattainability principle. The universe is basically telling us, nope, you can't go there. But that's only half the story. There's another, even stranger reason we can't reach absolute zero, and this one comes from the bizarro world of quantum mechanics. So, we've talked thermodynamics. Now, let's get weird. We have to dive into the quantum world to really understand what's going on.
Our classical, common sense idea of absolute zero is pretty simple. All motion just stops. The atoms would freeze in place, perfectly, completely still. But quantum mechanics has a very different answer. The reality is, atoms can never be perfectly still.
This leftover little bit of wiggling is called zero-point energy. And it all comes down to the famous Heisenberg uncertainty principle, which basically says you can't know a particle's exact position and its exact momentum at the same time. See, if an atom were perfectly still, its momentum would be zero. We'd know it precisely. But the price for that certainty is that its position would become completely unknown. It could be anywhere in the universe. To avoid that paradox, every particle has to keep a tiny little bit of motion, a permanent quantum jitter. So, okay, we can never actually get there, fine. But that just raises another question, right? How close have we actually gotten? The answer is just mind-bogglingly close. First, let's get some perspective. Let's look at the coldest natural place we know, deep space. The empty void between galaxies isn't at absolute zero. Because of the leftover heat from the Big Bang, the cosmic microwave background, the average temperature of the universe is about 2.73 Kelvin. And this is what's just so incredible. We haven't just matched the cold of deep space here on Earth. We have completely shattered that record. In labs right now, scientists have created conditions many, many, many times colder. Just how much colder are we talking? Well, look at these numbers. We're not in Kelvin anymore. We're not even in millikelvin. We're talking nanokelvins. That's billionths of a Kelvin. And even crazier, picokelvins. That's trillionths of a Kelvin. The current record, set in 2021, is a staggering 38 picokelvins. That is just 38 trillionths of a single degree above absolute zero. We are practically touching the bottom.
So we've established there is a bottom to temperature, but this whole journey leads us to one final, completely paradoxical question.
If nothing can be colder than absolute zero, could anything be hotter than infinity? The answer, and you're not going to believe this, is yes. And it's about to flip your entire understanding of temperature completely upside down. Okay, stick with me here. Welcome to the absolutely bizarre world of negative absolute temperature. Now, this only works in very special quantum systems that have a maximum energy limit. So think of it like this. At normal positive temperatures, most particles are in low energy states, kind of like marbles that have all rolled down into a valley. At what we'd call infinite temperature, they're just spread out evenly. But at negative temperatures, you get what's called a population inversion. Most of the particles are forced into high energy states. It's like finding all your marbles perfectly balanced on top of a hill, ready to fall. And here is the part that will absolutely mess with your head. Negative Kelvin temperatures are not colder than zero. They are, paradoxically, the hottest things that can possibly exist. If you put a normal positive temperature object next to a negative temperature one, heat would actually flow from the negative to the positive. That means the temperature scale isn't a straight line. It's a loop that connects back on itself at infinity. And you might be thinking, okay, cool party trick, but so what? Well, this could actually be a huge deal. See, in these weird negative temperature states, attractive forces suddenly become stable. They don't cause the system to collapse on itself. And some physicists are wondering if this bizarre state of matter could offer a clue to one of the biggest mysteries in the entire cosmos, dark energy. You know, that strange force that's pushing our universe apart against gravity's pull? Could the universe, in some strange way, actually be hotter than infinity? It's a wild thought, and to think, it all starts by asking what happens at the very bottom of the thermometer.